In this screencast, I want to give you an overview of the push relabel algorithm. And the goal of this is not to have an in-depth understanding of how the algorithm works, but more to just get an overview of how the algorithm works and some intuition about why it works. In order to really understand how it works, you should study the paper that I've posted on Canvas and read through the part of the paper that has to do with exactly how the algorithm is implemented. In order to do this, first let me just remind you where we are. We've already covered the shortest augmenting paths algorithm by Edmonds-Karp. There's another algorithm that we don't have time to cover that's interesting. It uses what are called blocking flows, or and it's by Dinitz. It's theoretically faster than the shortest augmenting paths algorithm, and in fact is generally in practice. But today I want to focus again on an algorithm that's theoretically the fastest of all these algorithms, and is also very good in practice, the push relabel algorithm. In order to understand the push relabel algorithm, you need to understand from a high level what the setup is. And the setup is, rather than working towards optimality, we're going to set up conditions on the state of the residual graph as we work through it, so that the condition of optimality is always satisfied, but the feasibility conditions to have a maximum flow are not satisfied. And the optimality condition that will enforce throughout the execution of the algorithm is number 3 here. There is no ST path with a positive residual flow in the residual network. So this slide just reinforces what I said on the previous slide. Most of the algorithms that you're familiar with maintain feasibility. In other words, they satisfy the constraints, and then the algorithm works towards optimality. But the algorithm we're going to do, push relabel, we're going to set things up so that throughout the execution of the algorithm, the optimality condition will be satisfied, namely no ST path in the residual graph at every stage, and will work towards satisfying the constraints. So we will have the algorithm will satisfy the capacity constraints, namely that the flow will be less than the capacity on every edge, but the conservation constraints will will be violated, and then we'll have to work towards getting the conservation constraints to be satisfied, namely that the flow into any vertex is equal to the flow out of any vertex. So how are we going to do this? We're going to fill up the edges all the way to the sink, and then if there's excess flow into a node, then we'll try as much as possible to send it downstream nodes, respecting the capacity constraints there. Now, once all the possible flow reaches the sink, then the excess flow has to be routed backwards towards the source in order to satisfy the conservation constraints at the vertices. So, and what happens with that, you can sort of think of it very roughly, as once you sort of got the flow worked your way back to a particular vertex in terms of clearing conservation constraints and having them hold, then what happens to do, you could either send the flow to another vertex if that's possible using different paths, and you keep doing that until eventually all the excess flow is routed back to the source. Sorry about that typo there, that should be source. So to add to your intuition about this, we're going to think of the edges as like water pipes or oil pipes, whichever you prefer, and we're going to have each vertex be at a height. So you can think of this as being in 3 dimensions, and the source vertex is going to start out at height n, and the sink vertex is going to be at height 0. And that's going to be maintained throughout the algorithm. We're never going to change the height of the source vertex or the height of the sink vertex. Then we'll impose another constraint that the flow can't go uphill at all. And it can only go downhill if the hill is not too steep. So again, sorry, that's a typo. If the hill is not too steep. As the algorithm proceeds, it's going to change the levels of the nodes to allow any excess to flow downhill. In the early parts of the algorithm, that will mean it's going to flow towards T. In the end of the algorithm, when it's trying to get the excess flow that's at a particular vertex, we turn things around and it will flow downhill back towards the source. So it turns out that there can't be an ST path in the residual graph of this network. If you think about it, it's because that the flow can't flow downhill the hill can't be too steep. And what that means, because the source is at height n and the sink is at length 0, that the path would have to be too long to be an ST path. It would have to have a cycle in it. Thus, this is the optimality criteria that we're going to have in place throughout the execution of the algorithm. And then, so once the conservation constraints are all met, then we now have a feasible flow, and it will, since it's still, there's no ST path, that means that we've got the maximum flow. So some definitions, and these are important, obviously, in terms of making sure that the algorithm is going to work. We're going to define an ST preflow, or a preflow for short. It's a function from the edges into the real numbers. And what does it mean? It means that for each edge, we still have our capacity constraints being satisfied. But for each vertex, we're going to have the condition that the amount coming in to V must be at least as much as what is going out. And the excess at E will be, we'll just write alpha F of V, and so that's the excess amount of flow that's at the vertex V. And the residual graph will work as before. So again, what we're going to do is we're going to maintain preflow, these relaxed conservation constraints, and we're going to work to convert it into a flow. So now all the conservation constraints will be equality. Okay, and again, we're going to do this. We're going to have labeling and a preflow F are compatible if we have these conditions on the source, the height of the source and the height of the sink. And in addition, this very important steepness condition that says for all the edges in the residual graph that h of v has to be less than or equal to h of w plus 1. In other words, so this is an edge from v to w, and it's saying that h of v can't be bigger than h of w plus 1. In other words, w can't be further down than 1 unit from v. So again, there's no ST path that's compatible with this labeling H. So the main thing on this slide, most of it I've said before, but the key thing really from an intuition point of view is just this last part down here, this part. Initially, the flow in every edge originating from the source is sent to the capacity. This enables, if you think about it, this enables us to get things off the ground in terms of having the source be at a height n, and then all the vertices are going to be at height 0. So this, having those edges be full, means that essentially you've cut the source off and got all the possible flow you can into the sort of initial vertices, thinking in terms of the ones directly linked to the source. And then what we do is we slowly raise the heights to enable the flow to flow down towards the sink. And we keep doing it. You think of this as a sort of a plane where we've got a wave going through it. In the nodes closest to the source, they're going to go up first. Then the next set of nodes are going to go up. And then depending on how the excesses are at each vertex, different parts of the graph will go up so that the excess can flow down towards the sink, which of course is at level 0. And then once all that gets down to the sink, once you're done sort of getting things down to the sink will slowly rise, and the rest of the vertices will come up as the excess flow gets pushed back to the source. So intuitively, it's kind of easy to see what's going on. The issue is how to implement it. So this slide gives the code for the push part of the algorithm. So remember, again, for the push, you've got to have excess flow at the vertex, and h of w has to be less than h of v. And in fact, since the edge has to be in the residual graph, h of v is going to be h of w plus 1. So it's going to go downhill slowly from v to w. So what do? How do you push the flow? Well, it's kind of like we did in Edmonds Carp. We've got this excess amount here, and we've got the remaining capacity in the edge VW. So you take the minimum of those two things, and then you augment along the edge here using delta. And you do that even if it increases the excess at W. So if VW is a forward edge in the residual graph, then of course you increase the flow by delta. If it's a backward edge in the residual graph, then you decrease the flow by delta. This will be more relevant as we're pushing things towards the sink, right? There'll be forward edges, but then as we push the excess back towards the source, they're going to be backward edges. And then we have the relabel subroutine. That's easy. This basically happens if you have excess in a vertex, and h of w for all the edges adjacent to v, h of w is bigger than h of v. So in other words, they're all either level or uphill from v. So if that's true, then you want to increase the height of v by 1 in hopes that you'll be able to push the excess that's in v to one of those other neighboring vertices. And then the push relabel, the main part of the algorithm is simple. First, we initialize all the vertices' heights to be 0 except for the source, and we initialize the source to be of height n, which is, of course, the number of vertices in V. And we initialize all the edges coming out of the source to be at full capacity. And otherwise, all the edges will be 0. So notice all the target edges here, all the target vertices here are going to have excess flow at them. So then here's where the work gets done. While there exists a V that's not equal to T, and the amount of flow at V is bigger than 0, in other words, it has an excess, then we find the node with the excess, the nodes at maximum height. So if there is a W, such that the preconditions hold for push V, in other words, V is at height W plus 1, then we push. Otherwise, we relabel V. Notice we know that if the precondition doesn't hold, right, then the height of V has to be less than or equal to the height of W. So it's all right to increment the height of V and not violate the setup for the height function. So it's time to move on to an example, and we'll work through it. But I just want to emphasize one more time sort of the cleverness and unusualness of this algorithm compared to all the other algorithms. We're maintaining this optimality condition by setting up the residual graph in a certain way that depends on this height function, and then we have to maintain that optimality conditions and work towards feasibility. So here's the example I want to walk through. It's a really simple one. I think it's in the paper that I put up for you to read. We just have 4 nodes. These are the capacities, as usual, on the edges. Okay, so the first thing the algorithm does is initialize the heights. So there are 4 vertices. So the height of the source is going to be 4, and the heights of all the other vertices are going to be 0. After we've done that, we initialize the flows that come out of the source. Okay, so we saturate this edge with a unit of 1, so it's at full capacity, and we saturate this edge with a flow of 100, so it's at full capacity. So now, what does that mean? That means that the excess at V is going to be 1, and the excess at W is going to be equal to 100. Okay, so at this point, W used to be at 1, but we're going to increase its height to 2 now. And so this edge is full, so there's nothing you can do here. But there's a forward edge here that will hold 1. And remember, there's a backward edge here with 1 on it. So W is now going to be at height 2 when we raise it. And we're going to be able to send 1 unit down the forward edge and push another unit back on the backward edge. And so now V is going to end up with an excess of 2, and W will be left with an excess of 98. So I suggest taking a couple minutes and going over this slide and make sure you see exactly what's going on and how you get from one picture to the next. So now, where are we? We've got an excess of flow at V of 2 and an excess of flow at W98. So we're going to keep working on W. And so W can't push any more flow to either V or W, or V or T. So what W is left with is a backward edge to S. The backward edge to S has capacity of 100, but W's height is only at 2. So what we're going to do is we'll do 3 relabels of W, and we'll get it up to 5, and then we'll be able to push back the excess from W to S, and that will give us this picture. So we pushed back the excess of 98 back to S. That means the resulting flow from S to W is 2. Okay, W is a height of 5, and the only node with excess is V, and it has an excess of 2. So now we're back at V. It has an excess of 2 units, and if we look at the height of V, its height is 1, the height of T is 0, so we're able to send those 2 units from V to T. Okay, and so now we have 2 units of flow from V to T, and notice now all the excesses are 0. So we can terminate the algorithm, and we know we have the maximum flow because by looking at the cut SW and VT. So that, what will that be? That'll be the edges, this edge, and this edge. So using the idea of flooding vertices seems like natural, but we have to use this height function and invariance to enforce the no ST path optimality condition. This is not intuitive. It took a long time for computer scientists to find this. So if you're finding it difficult to get your head around this, don't worry, you are not alone. The analogies for finding the cut, the min cut, are a little hard to see, but basically you can find it easily enough by just running the shortest augmenting path once on the residual graph. Of course, the shortest augmenting path won't find anything, but it will label the vertices as usual, and those labeled vertices versus the unlabeled vertices tell you what the cut is going to be. The performance is big O of n cubed, and in practice it's really fast. Basically, the way you do this is a little tricky using what's called the level or layered graph, and you show that the number of pushes has bounded above by n cubed, and the number of relabels is bounded above by n squared. The one issue of implementing this efficiently is that you have to find the excess, the vertex with the maximum excess on it in constant time at different places in the algorithm. And that can be a little tricky. It's not that hard, but you'd have to think carefully about how you're going to do it. So that's it. Hopefully this gives you the intuition that will help you read the paper to understand the details of how the algorithm all works. Again, I don't expect you to take away the details just by listening to the screencast, but I do hope it will be a big help for you in trying to understand what's going on and being able to understand why the algorithm works.